Hello and welcome to this BioProcess International Ask the Expert webcast. I'm your host, Leah Rosen, online editor for BioProcess International. Before we get started, just a couple of notes. This webcast is being recorded and will be made available for replay in the multimedia section of our website. We've muted the audio lines, but we welcome you to type in your questions for our speaker in the question and answer window on your screen. After the presentation, we will begin the question and answer portion, and I will ask our speaker your questions. Your questions in the question and answer window will only be visible to myself and our speaker. So thank you for joining us today. It is now my pleasure to introduce our speaker, Dan Yukon from Astrea Bioseparations.
Hello?
Yeah, go ahead, Dan.
Oh, I was disconnected for a quick second. I apologize. Hello, everybody. Thank you for attending. My name is Dan Yukon from Astrea Bioseparations. I just wanted to thank everybody for attending this presentation. I hope everybody's staying safe through this difficult COVID time. It certainly has been a very interesting and challenging year for all of us. Challenges that we've never faced before, and hopefully we're winding down. So again, thank you for your participation. Before I get started, I just wanted to mention that the opinions and ideas here are my own, and so I just hope you take that as a grain of salt. So a little bit about myself. I am the head of sales, regional sales North America and global SNAP sales for Astrea Bioseparations Company. I was the former president of Essential Life Solutions, located in Stoughton, Massachusetts. I founded the company back in 1999 and have been in chromatography ever since. The company was recently acquired by Astrea Bioseparations, and I've assumed the role of head of sales and marketing for North America. And so a disclaimer before we get started, I am not a scientist, so any and all of you who have come here looking for the answers to your deepest chromatography problems probably will not be solved during this presentation. So I just wanted to kind of jump in and talk about the topics that I wanted to cover during this presentation. So I've kind of broken them down into a couple of sections, general considerations and commercial considerations. And as we go through the presentation, I'd just like to say that what we're doing is we're talking about ideas and considerations when you're selecting columns. This is not a tutorial on chromatography. This is more for those that are trying to determine what hardware selection they should be making for low pressure applications. And typically in these low pressure applications, our columns tend to be glass or plastic. And this is also the new age where people are buying pre-packed columns. And there are still a fair amount of you folks out there that are packing your own and are experiencing those challenges of packing your own columns. So this is kind of where I'm addressing the meat and potatoes of this presentation. So, and I'd like to keep it, very casual as we move along here. So my background is mechanical engineering, and in mechanical engineering, 1 + 1 always equals 2. And it seems like in chromatography, 1 + 1 doesn't always equal 2, it equals something else. And we're constantly being approached by scientists that are struggling with what seems to be a very easy logical process. I call it like baking a cake. If you put the same ingredients in the same bowl, mix it the same way, put it in the oven, you should expect a cake. But it always seems that there are other factors involved. Sometimes it's the technique of the operator. Sometimes it's the resin formula that's been received. It can be the buffer mix that the resin is received in. Many variables come into play, and many times people come back to me and say, this is just, it's like a black art. I feel like an alchemist when I'm trying to do my chromatography. So what we're trying to do here in this presentation is to somewhat demystify the selection of the column, and I'll go into a little bit about the packing of the column and the qualifying of the column. So we'll pretty much stop at that point, and we'll allow the chromatographers to do their chromatography after that point. But there seems to be a lot of confusion, a lot of misinformation, and a lot of just general knowledge that people don't take into account when they're looking at selecting their column hardware. There is a lot to pick from out there in the marketplace. So I just thought I would go into some of the considerations that people should take as they're considering their columns. So the first thing that we like to talk to folks about when they're selecting their column hardware, the real kind of core starting point is volume. We have a volume of resin, and that volume of resin has to capture a certain volume of our sample. Different resins capture different volumes of sample. So we suggest strongly that the real core starting point would be, once you understand what you're trying to collect and how much of it, and you are maybe able to select the finalist in whatever particular resin family you want to consider, talk to that resin supplier and explain to them, this is what I'm trying to capture, how much of it, and then they can steer you in the direction of volume. And volume is it's a value of how much of the resin that you're going to end up with in the column. Now, one of the things that we do look at is aspect ratio. And aspect ratio in your column is the ratio of the diameter to the length. So for any particular given volume, we can have a tall, skinny column. We can have a short, fat column. The short, fat column will allow the sample to generally travel faster through the resin bed that we've packed. And that sounds really great because it's going to slow down the residence time in the column. But by the same token, if we're doing size exclusion type of application, it's extremely important that the sample has an appropriate amount of resonance time to interact with the chromatography resin as it's traveling through. So there is no hard, short answer to, do I need a short, fat column or a tall, skinny column? Again, the recommended starting point is to talk to your resin supplier and understand for your given volume of capture, what is the best configuration of the column that we want to look at. Columns come in many diameters and many lengths. And so we want to take a look at, that aspect ratio to understand which way we're heading with that. The other thing that is important to consider when we're looking at aspect ratio is flow distribution. So if we have decided that we want a short, fat column, we typically have an inlet connection that's at the top center of the diameter. And if we don't have good flow distribution in that particular column, we're not going to get good chromatography because the sample and the flow is going to want to impact through the center of the bed and not react with the full diametrical availability of resin that's there to do the work for us. So when we are considering shorter, larger columns, the idea that our flow distribution is an extremely important aspect to the design of the column that we're going to choose. So when you're talking to your potential column vendor and you have a large diameter column and a relatively short bed height, spend some time and talk to them about the flow dynamics of the column. Explain how the flow goes in, how the flow is distributed across the bed, how the flow is collected at the opposite end of the column and accumulated, and it ejects from the bottom of the column. Conversely, if we have a tall, skinny column, then we have wall effect issues to deal with that come into play in the interaction of the flow dynamics through the column. So I gave a little chart off to the right here. It's more towards gaseous flow, but there are drag coefficients that come into play in a column that has a lot of wall area that could impede or affect the flow of the chromatography and your sample down to the center of the column. So that's really where we feel, a good starting point is when we're thinking about, purchasing or speccing out a column for our application. So the next thing that I suggest people look at is pressure considerations. We, as chromatographers, we're doing many different types of chromatography in open top containers with gravity flow, in sealed containers with resins of large diameter pore size, particle size, small diameter particle size. And the particle size, in most cases, is driving the back pressure through the column. And we want to understand, for the resin that we have decided on, is it very large particles of resin that provide minimal back pressure, in which case our column maximum operating pressure is not as big a consideration. If we're looking at resin which has much smaller particle sizes, it's going to drive the pressure, the back pressure for flow up dramatically. And we can't arbitrarily take a column and just unpack it because it had some 90 micron resin in it and decide we want to put 10 micron resin in it and run it. We're clearly going to have some flow and back pressure issues. So again, we should be very cognizant of the fact as we go through the selection of our column, what is the back pressure? And back pressure, as it's coming up, is going to create a potential safety issue. If we are setting our pressure limits on our system, we clearly need to understand what the pressure limit of the column is. Now, I know some column manufacturers post a maximum allowable pressure of their column. That is the pressure that is close to the fracture point of the column. And if we're running our process or our purification and we have a pressure spike, even if it's a minimal pressure spike, it can exceed the pressure cutoff quickly of where we set the system pressure. I've seen many cases where we have set the maximum pressure for our system very, very close to the operating. We get a pressure spike, the column fractures, and we have a catastrophic failure of the column. Now, because of the fact that columns are flooded with liquid liquid, as we know, is incompressible. We don't build up a lot of dynamic pressure. There generally is not as much of a safety issue for a dynamic explosion of a column, although, in my opinion, all columns should be covered and protected from the operators. And so in our own lab, when we're working on columns and we do have a fracture, oftentimes it's very anticlimactic. The glass cracks or the plastic cracks, the resin spills out, the pressure drops immediately, and then we clean up the mess and we start all over again packing our column. We've seen other incidences where we're running very low, small diameter resin at very, very high pressure, at relatively high flow rates or some higher flow rates. We do have a fracture failure, and it tends to be somewhat dynamic and can be a safety issue. So in our opinion, not only all columns should be protected in some way from the operator, but also we should understand, what is the failure point of that column? Is it 5% over the stated pressure by the manufacturer? In the case of our own products, we test the products all at 1.75 times as a non-destructive test, all columns that ship out the door. Columns that are made from glass, even though they can be appearing to be without any kind of impurities, dents, dings, cracks, there is inherent stress that is residual from the manufacturer when the glass is made. The glass is normally annealed, and you cannot see the residual stress inside of a column. Here in our own lab, we have special tools where we can create visibility of that internal stress. But oftentimes, even though we can take a column and test it, it appears to be fine. It can fracture unexpectedly, and when operating columns for safety measures, we should always be cognizant of the fact that safety is number one. Also, as I had mentioned at the beginning of this presentation, columns for purposes of this discussion can be either glass or plastic. Glass obviously is much more fragile and brittle, and when there's a failure, it tends to be more of a dynamic failure. Plastic will tend to crack and relieve its pressure. But in any case, we want to understand when we're selecting a column, are our buffers, both our packing buffers, storage buffers, cleaning buffers, are they all compatible with the materials that we have in our column? So we want to take a look at that and talk to the manufacturer. We want to look at solvent compatibilities. And even at some times we want to consider temperature in the selection of our column, whether the temperature range that we anticipate will be okay for the application that we've selected. The next point I wanted to talk about is the connections to the column. Oftentimes when people are purchasing columns, they're concerned about what is the connection available for my column to my system. Fortunately, as time has gone on, most of the manufacturers of FPLC systems have standardized their connections to the manifolds on the systems. So what we see these days mostly is 1/16 finger tight for smaller columns, or 1/4 28 finger tight for larger columns. And most of the columns that we sell or see tend to either be 1/16 or 1/8 inch. So in the case of our product line, we would recommend for a 1 centimeter column or 1.5 centimeter column, typically for the flow rates that we would anticipate, about 1/16 would be normal, although we do see the larger columns sometimes run at those smaller tubing sizes. The larger columns of 25 millimeter diameter and larger typically are 1/8 inch, in the standard systems and lab scale columns that we look at. So in this particular slide, the tan fitting is a 1/16 finger tight. The only drawback to those particular connectors is they're dedicated to 1/16 only. And a lot of the newer active systems are plumbed in the manifolds for female 1/16 ports, so they tend to be more universal. Columns, on the other hand, can have that 1/16 female on it to accept that fitting. In the case of our snap columns, for instance, we have the 1/4 28 system, which is that blue connector. And for all of our columns, we can use a connector interchangeably be either 1/16 or 1/8 inch on the same column. So it's got a little bit more flexibility on the column connection end for the folks that are trying to make up those connectors. The next topic that I'd like to cover are frits. Frits, as we all know, are the device. Every column has one. Its function is to allow easy pass-through of the liquid in question, the buffers, our chromatography buffers, and our injection. But they also are very important to hold back the chromatography media that's inside the column. So we oftentimes walk a very fine line between looking at our frits and deciding, well, we want the maximum possible frit porosity because we don't want to restrict the flow through our column by having too tight of frit porosity. But on the other hand, when we look at a lot of the resins come with a pretty broad range of particle size. So for instance, a 40 micron particle can be purchased from a supplier. And when we look at it, it's 40 micron average particle size, but the range of particle size could be 30 to 60. So if we pick a frit that has too large a pore size, assuming that everything's 40, our fines and smaller particles are going to jam those frits up. We're going to have flow restrictions, and we're going to have complications with our chromatography. Conversely, if we want to take the more conservative route and go with a very fine pore size in our frits, we will find that we have a much higher back pressure, and we have that obstacle to deal with. So we would talk to our customers when people come to us and find out a little bit more information about what resin you're using in your columns, what flow rate you're expecting. And frits also come in different materials. They can come in polyethylene, they can come in stainless steel, some come in sintered glass, some come even in titanium, or even other materials, depending on what your running and storage buffers might be. We find, as a general rule of thumb, for most aqueous applications, polyethylene frits are generally well accepted and hold up quite well. They're also easily interchanged in the columns. And for more aggressive solvent applications, we typically step up to stainless steel or sintered glass or in extreme cases, titanium. And again, those are rare and far between, but we do have those applications from time to time. So the awareness should be there, what I'm doing, what my flow rates are, what my resin average particle size is, what the maximum is. And another key thing when we're preparing our resin to be packed in the column is we highly recommend defining all the resin. So when resin is shipped, it develops fines from its shipping and maybe hard handling, sometimes due to just common carrier shipping. And it's very wise to define the resin. That way, plugging will be avoided in the frit porosity structure. We oftentimes have people asking us, does it make sense to take frits out from time to time and sonicate them and reinstall them? We in our company and in our viewpoint, look at frits as a consumable item. So in our case, we recommend every time a column is repacked, there should be some serious consideration to changing it out for new, as opposed to trying to clean it. There could be some carryover from the prior batch or prior campaign in that column of some carryover material, or just some carryover pluggage that will not be relieved by sonicating or other cleaning methods. And we look at it as cheap insurance to basically replace those components. Frits and O-rings we look at as normal replacement when we pack in a column. So the next thing that we look at is testing and qualification. And testing and qualification is extremely important to the process as we're getting ready to do our chromatography. After we pack our column, and typically most of you folks, I would imagine, will be flow packing your column, we have to prepare the column and do an evaluation. So the evaluation is typically done by some test sample run through the column. And in the case of most aqueous resins, it normally takes the form of a high concentration marker of sodium chloride, or it can be acetone. So the column is set up on the test stand, and we would run through a test injection, and by using some sort of detection, we would monitor the efficiency of the flow of that test injection through the column. Typically, our test criteria, as you probably are aware, is asymmetry and plate count. So those are the values that we kind of live and die by as scientists in preparing the column. And we cannot stress highly enough that the values of the testing of the column should be within the accepted criteria that's set forth by the manufacturer of the resin. If those values are outside of the accepted criteria, and you try to run your chromatography after that, we really feel that your results are going to be in question, and more time should really be spent getting the column qualified within the column acceptable range considered by the resin manufacturer. So, in the slide, I've stated kind of garbage in, garbage out. So if you try to take a shortcut, it'll come back to haunt you. It's really the work needs to be put in on the front end. The resin slurry mix has to be correct. The flow rate has to be correct. The compression factor, if there is one in your resin, has to be correct. And your evaluation criteria has to be correct. So we, again, strongly suggest staying within the boundaries of what you've set for yourself and what the manufacturer has set for packing the column and getting it qualified. So, of course, price is always a consideration when selecting your FPLC columns. Column prices range, all over the place from different manufacturers with different levels of sophistication, from an open-top glass tube to a pretty high-pressure device that's going to work with some of the smaller, more high-performance resins. We feel that in an academic environment where we're training students and results are not that important, we're just trying to bring across the point of how the techniques of chromatography are being done. Open-top gravity columns, gravity settle columns, they can work fine, and they have the added benefit of safety because it's not a closed system where the student, if they're not paying attention or have not set their system pressures appropriately, they're not going to run into a problem where they're going to create a failure on the column. When we get into the real lab in the real world, and we've spent a lot of time packing our column and preparing our column. Our sample has gone through a number of steps before it has come to us for purification for the step that we need to do. There's a very large investment in that sample that we're going to process. We feel that relative to the cost of the sample, the interest should be placed in the performance of the column rather than the actual cost of the column. So here and again, we go into many labs. Scientists are using what we feel are inferior hardware for performing very important purification steps, and they're really fighting the hardware. And we can't stress enough that the hardware is your friend. It's a tool. I kind of liken it to cutting a tree with a dull saw. You'll get the tree cut down, but it's going to take twice the amount of work, and you're really fighting the hardware. So if you're using good rock-solid hardware, you're going to get a good rock-solid result, and you're going to get a consistent result. And that's one of the things that we try to tell folks, that repeatability is very important in the work we do, and the hardware should give you good repeatable results. So it's important that the hardware selection should be taken into account with the performance in mind. Also, when looking at the hardware, I had spoken earlier about the maximum pressure limit of that hardware. Clearly, if you're considering packing a small diameter resin, you need to be very cognizant of the maximum pressure rating of the column in particular, and the frits that are there. So the next thing that I wanted to discuss is when we're in the lab, we may be working in isolation where we have only one purification to do within our group, and we're working kind of autonomously, and our result is our result. And we may be working on that similar size types of purifications over and over again. But again, we could be in a different situation where we're on a scale-up path. We're on a process development project. And we have to think about, where we're going with this purification. Oftentimes, the scientists will perform qualifications and purifications at a very low scale, and they're handing it off to another group. I believe it's incumbent upon the folks doing the smaller scale purification to have some respect and understanding of who's the next group that's going to get this and what are their challenges going to be. And before I select a specific column, have I talked to the column manufacturer and understood, do they have a product that is going to accommodate my scale-up team? Or is my scale-up team going to have to start all over again and use my SOP and adapt it to somebody else's larger hardware that may not be so scalable and give results that are not consistent with what's been handed up the ladder. So we feel it's very important that look at the big picture. Look at the big picture. So the other thing, when we're selecting columns in a small lab, particularly a lab that has a low budget, this could be counterintuitive a little bit, but we oftentimes have customers coming to us and our particular product line has a very high pressure tolerance. And they say, well, I can buy a cheaper column that has a lower pressure tolerance. That's of course true, but in a lab where there may be some considerations for budget, oftentimes in academia, we're going to finish that project and we're going to put that empty column in a drawer and someone else is going to need to use it. Well, that next experiment might call for a higher pressure tolerance column, and rather than going out and buying another one, we could reconfigure the frits on the column that we have and put it right into service for a higher pressure application. So we can always go up in pressure, but we can't always go down in pressure. So I think that's something particularly for smaller labs, that you can develop a familiarity with a column family of products. And I think that familiarity makes the job easier when you go to set the column up. What are the challenges to packing the column, mounting a packing adapter, configuring the column, how it runs, how to mount frits. I think just selecting a column that has a higher initial pressure tolerance than you might even need indicates that the column is built with more robustness and will be more durable over the long run, but also has more flexibility in the lab. So again, just be sensitive to your colleagues in scale up or in the lab, maybe that might need that column for something else later on. So just kind of wrapping up. There are many columns out in the market that are, for selection, and they're all good for their specific use. They were designed for specific applications. So I think the best thing to do is, when you're considering columns for your application, take a good hard look not only at what you're going to do today, but what you might want to consider going forward, and what your colleagues, the guy in the next bench from you, the person in the next bench from you, what they might intend to do. And, interchangeability, if you are setting up the lab and you want to go in a particular direction, you will start to develop spare parts, you'll start to develop extra components, longer glass, shorter glass. Are the parts interchangeable with each other? What is the flexibility to reconfigure a column? Where are we going to be heading tomorrow? And we feel that if you stick with one particular brand and are very happy with it, and it represents some flexibility for you, it ultimately is going to give you the best value going forward. So when developing your methods, and you're going to hand them off, think about the trajectory of what you've chosen and why. So with that said, I think I'm ready to open up for questions. Again, this topic is very broad. It has many tributaries, and there are so many different columns and so many different applications. It's hard to cover everything in one presentation. My contact information is on this last slide, and I would encourage anybody to reach out to me directly if you have any specific questions. Thank you.
Thanks, Dan. So we do have a couple questions. What are the most common rookie mistakes you see among your scientists when selecting or using columns?
So that's a good one. What we find is, particularly in academia or smaller labs, somebody has been given a task to perform a purification, and they need a column. They go to the drawer, they open the drawer, they look through the drawer, they grab the first column that looks close to what they need, and they proceed to try to pack it and don't really understand what's there necessarily. They assume a diameter, maybe the diametrical tolerance of their column. They may not even change the frits from the prior user, or not understand that the frits are not appropriate for the application that they're trying to achieve. And they spend a lot of time with preparing their resin and packing the column, and then they get a very poor result, and that's when sometimes we get a call. So really, I think the best thing to do is stop, really kind of understand what you've got for hardware, and look at the application that you're trying to fulfill, and then proceed forward carefully and slowly and methodically.
Okay, and what are some good resources to use when selecting columns?
So we feel that the two best resources to use are if you are able to identify the resin that you would like to pack, get a hold of that resin manufacturer, ask them if they have any hardware, especially if you're buying bulk resin and you're going to pack your own column. If they have any hardware recommendations, or if they know of any application data that's available to review before you get started. The second thing is develop a relationship with a column supplier. In particular, if your lab has columns in it, or you've heard of a column that you're interested in using, get a hold of that column manufacturer. And it's always good to have a three-way dialogue between the scientist, the column manufacturer, and the resin supplier. We as a column supplier often work in that three-way dialogue, and we're able to troubleshoot even before the work begins to have the best possible results, on the first try, or at least the second try.
Okay. Well, thank you, Dan. I think we're out of time. If you enter your questions, we'll be passing those on to Dan directly, and he can follow up with you after the webcast. So the recorded version of this webcast will be available for on-demand viewing on our website. As a registered attendee, you'll receive a follow-up email providing you with a direct link. We look forward to having you join us at future BioProcess International Ask the Expert webcasts. Look for those announcements in your inbox. Goodbye.